So let's start in subtask 2. In subtask 2, we'll be creating a back-to-back MC-lag multi-chassis aggregate Ethernet interface on both sides between virtual queue of x1, queue of x2 as a side number 1 and virtual mx1, virtual mx2 in side number 2. So we will be establishing ICCP session. The ICCP will use the IRB addresses that have been configured previously in Vlan 44 and Vlan 45. Virtual MXs to forward traffic to queue of X's with minimum of 20 gig available capacity back to back. This means actually we need to have at least 20 gig of bandwidth available at any point of time between the virtual MX and virtual queue of X. So this will lead to have the MC lag in active. All links are in active mode. The multi-chassis aggregate Ethernet should pass VLAN 100. So the multi-chassis aggregate Ethernet should pass VLAN 100 end-to-end till the server. So we need to configure the interfaces towards the server for VLAN 100 in a trunk mode. Configure IRB for VLAN 100 between virtual MX1 virtual MX2. So we need to configure VLAN 100 back-to-back in VMX1, VMX2, and configure this IP address 192.168.1.254 as the IP version 4 gateway using Anycast IP. Anycast IP, which means no VRRB is configured, and we will use the same IP and MAC on both sides of the MX routers. Configure VLAN 100 between MX1 and MX2, which we already should be configured in this the previous step, with IP version 6, this IP version 6 address using VRRB, and allow IP version 6 to respond to ping. So in VLAN 100 and under IRB 100, we will configure both IP version 4 as a gateway for the servers and IP version 6 as a gateway for server. For IP version 4, we'll use Anycast. For IP version 6, we'll use VRRB. Let's start by the task and the virtual MX side. So let's configure VLAN 100 in the back. Let's configure, create the ICCP. So we'll use local address. This is the local ICCP address, and let's configure the peer. Okay, for the ICCP, we need at least to configure liveness detection, multiplier of 300 milliseconds, multiplier 3, minimum interval 300 milliseconds, which is 3 seconds. Actually, liveness detection or the ICCP liveness detection is based on BFD. The ICCP itself does not have its own kind of keep alive or hello. Actually, the ICCP is fully dependent on BFD for the keep alive. Set redundancy group list equal to 1. Actually, there is no ICCP authentication required. There is no kind of split horizon, split brain backup detection required. So here we will not configure authentication or will not configure backup detection. Let's don't forget to configure the service ID for the ICCP. Then we will configure the aggregate Ethernet interfaces towards the queue of X's. Let's go back to the diagram. So from MX side, we need to configure 002, 003. Okay. So we'll assign post 002 as a part of EE1, and we'll assign Giga Ethernet XE003 as a part of XE1. We'll use LACP in active mode. System ID. We'll use statically configured system ID. Then we'll configure the multi-chassis Ethernet parameter. So here we configured set mode active. So here we configured the multi-chassis aggregate Ethernet ID number 1, identity group number 1, which is this two parameters common between the MXs. Then chassis ID 0, other MX chassis ID 1, status control active, other MX status control will be standby. Here's the LACP admin keys missed. So let's configure set LACP admin key equal to 1. Okay, so we configured the aggregate Ethernet parameter. Let's enable VLAN 100. Let's configure AE0 as a trunk interface. With VLAN member of 100. Let's configure VLAN 100 bridge domain. And layer 3 interface of IRP 100. Then there is a very important configuration command is to enable the ISL configuration, the inter-chassis link protection. So we need to configure the peer IP. And the protection interface is AE0. Okay. As we configure the protection interface to be AE0, and also we need to run VRRP in the AE0, so we need to enable VLAN 100 in the back-to-back interface. Here we need to activate to enable VLAN 100 under this trunk. Okay, so we have now enabled VLAN 100 in the back-to-back, and we enabled VLAN 100 in the multi-chassis aggregate Ethernet interface towards the queue of X's. Then we need to configure the IRP interface. We need to configure the family INET address. This IP address. This IP address is any cast, so we'll configure this IP and same MAC on both sides. So this IP and MAC will be replica on both sides. Then we need to configure family INET 6 in a VRRP. So this is IP address of the VIP. This is the VIP address. So we need to assign each MX unique IP address. So I'll use here 25. Sorry. I'll use here 251. VRRP, let's use group 100, virtual INET 6 address, and we'll use here the VIP address of 254, and then we need to accept data just to control which router will be the primary or the master for VRRP. I'll just set the priority here 210. However, it's not required, but there is nothing will be harming instead of relaying in the kind of type breaker of lowest IP address. So I'll just set the priority in a manual way to control the VRRP mastership. Okay, so here is the VRRP configuration. Let's check the configuration. So first of all, we assign 002 and 003 to aggregate Ethernet 1. Then in the aggregate Ethernet 0, the back-to-back interface, we enabled VLAN 100. Then we configure the AE1, the multi-chassis aggregate Ethernet parameters. Here is chassis 0, status control active, then mode active redundancy group number 1. Under the LACP, we assign a statically configured LACP that should be shared between Mx1 and Mx2 towards the virtual queue of X's. Then we configure the IRP interface VLAN 100 for IP version 4 address, which is the anycast IP, and the IP version 6 address, which is a VRRP. So we need to change the unique IP address between the MXs while keeping the VIP address is the same. Then we enable the multi-chassis configuration, the ICL protection link. Then we configure the ICCP, and we configure the bridge domain and enable the service ID for the ICCP. So let's take this configuration and modify to be applied in MX number 2. XE002 and 003, exactly the same in both sides. So in MX number 2, here is 002, 003 as well. So there is no changes here. And then in Aggregate Ethernet 0, we will add VLAN 100. Then in Aggregate Ethernet 1, we will use the same parameters for the LACP and admin key. However, we need to change the SASE ID to be 1 and the status control to be standby. Then the trunk interface towards the virtual queue of X's will have VLAN 100. Then in the IRP interface, the same IP version 4 address will be used. However, in the IP version 6 address, we need to have different version 6 address. So we'll use 252. We will keep the same VIP. Let's remove the priority. So the default priority will be 100, and this virtual MX2 will be backup, Vrrp backup. For the MAC address, this is actually need to be shared between the two MX nodes. For the multi-chassis link, we need to change the IP address to point to the peer router, which is Mx1 here. Then in the ICCP local IP will be 45.1 and the peer will be 45.0. The same configuration for the redundancy group and live detection. Then the same bridge domain need to be configured on both sides and service ID. Let's go and apply the configuration. Okay, now let's see the IRP interface. Okay, for the IRP interface 100 is being brought up. For sure, we cannot use the IP version 4 for reachability test. So let's use the IP version 6. Let's run the 251. Okay, so here's looks we forget to commit in this side. Okay, let's go back here. Okay, now here is the IP version 6 reachability, which means that this back-to-back link AE0 have VLAN 100 enabled, and the VLAN 100 have the proper reachability. Let's see the ICCP. Okay, for the ICCP session, it is being established and up between Mx1 and Mx2. Now let's see the LACP interface. AE1. AE0 is the back-to-back interface, actually is being working for, and the status is collecting, distributing. AE1, the interface towards the virtual MX, is still in detached because we don't configure the virtual Q of X side yet. Let's do the same. Okay, so it's the same for AE1 here. Let's configure in the Q of X side. So in the Q of X side, in Q of X, both interfaces 002, 003 and both Q of X's will be assigned to the same multi-chassis aggregate Ethernet interface. Also, we need to enable the ICCP back-to-back, and we need to enable bridge domain 100 or VLAN 100 and assign this interface towards the servers and the interface uplink towards the MXs as a member in VLAN 100. So let's start with assigning interface 002 and 003. To aggregate Ethernet 1. Then edit interface EE1, aggregate Ethernet option. We'll use LACP active and assign a system ID. This system ID should be shared between Q of X1, Q of X2, and it should be different from the one that we assigned in the MX side. So I'll use this one. Then we'll configure the aggregate Ethernet parameter. Then let's configure the ICCP. Here is the ICCP. ICCP will be running in the back-to-back interface over VLAN 44. Here is our local IP, and then our peer VRP44.2. Let's enable the service ID number 1. Now we have been configured the ICCP. We configured the Aggregate Ethernet interface. Let's configure VLAN 100. Let's configure VLAN 100 in the Aggregate Ethernet interface in the back-to-back Aggregate Ethernet in the Ethernet interface towards the MXs. Okay, and let's as well configure the server facing interface XE001, which is this one. Okay, so now we configured the interface towards the server to be trunk in VLAN 100. We configure the interface towards the virtual MXs to be trunk in VLAN 100. We configure VLAN 100. We configure the ICCP. Let's configure the ICL. Let me check if I do configure the ICL or not. Let me configure the inter-chassis link. So the IP of our peer is 44.2. Protection interface is AE0. So here, let's review the configuration. The interface 001, which is the server-facing interface, is enabled to be in a trunk mode with VLAN 100 towards the server. XE002, 003 are assigned to Aggregate Ethernet 1. Aggregate Ethernet 1 is an LACP. We enable the LACP and we configure the system ID and admin key statically. Then we configure the multi-chassis parameters. Here is the multi-chassis ID is 1 on both sides, redundancy degree of 1. Chassis ID should be 1 in virtual queue of X2. Then status control should be standby. Then we configured this interface to be in a trunk mode towards the MX routers. Then we configure the ICL protection. Then we need to change this IP address to be 44.1. Then here is the configuration of the ICCP. The local IP will be 44.2 and the peer IP 44.1, and everything else will remain the same. So let's go here. Let's commit here and commit here. And show ICCP. Let's see the ICCP. Now the ICCP getting established. There is no actually backup it should be up. This is the liveness detection. Okay, liveness detection is up, and both the Q of X1, Q of X2 showing redundancy group number 1. Let's see now the Aggregate Ethernet interface towards the MX. So the Aggregate Ethernet towards the MXs is Aggregate Ethernet 1 is being now up and been collecting, distributing. So let's see the extensive to see the LACP system IDs. So in AE1, the actor, which is the local interface parameters, XE002 and the XE003, both of these interfaces are using the same system ID, LACP system ID, and from the partner side, it is using this system ID, which is ending by 0512, which is a system ID we assigned to the MX nodes. Let's see it from the Q of X2 side. Make sure as well both interfaces are up. Here in AE0, actually both interfaces XE002, 003 is being actively collecting and distributing. and here the partner side, which is the MX side, post links 002, 003, having the same system ID. So, and from our local side, we are using 0612 in both interfaces and in both QFXs. So now we have a back-to-back MC lag between the virtual MX and virtual QFX. At that point, we need to make sure that our servers can reach the gateway. So from our servers here, we need to make sure they can reach the gateway. So let's test. So our servers here, let's see what is the configuration of our servers. So let's see this interface. So this interface is using 192.168.1.1. Let's see this from the server 2. Let's see this interface configuration. So the interface is 192.168.1.2. So here this server is 192.168.1.1. This is 1.2. Let's make sure this server can reach the gateways. So let's see if we can reach 254. Okay, we cannot reach 254 from server 1. Let's make sure we can reach from server 2. Okay. Let's make sure if we can ping server to server. So from server 1, let's reach server 1. So there is no connectivity at all between the server or the gateways. Actually here I did kind of missing configuration intentionally, just to show a change between this setup and the other setup. In the other setup, or the chapter 1, if you remember, we mentioned in chapter 1, we don't need, in chapter number 1, actually, if you remember, in the back-to-back interface between QFXs, let's go to the diagram of chapter number 1. In the back-to-back interface in the QFXs, I mentioned that if we enable these VLANs, which is VLAN 10, 11, 12, that is for the server sides, if we enable this VLAN here and here, there will be a kind of a switching loop, because when the traffic goes from the server towards the QFX will send to its peer QFX in the ICL link, and then the other QFX will send the traffic up, because this interface, this aggregate Ethernet interface, is not the same as this one. So the QFX will send the traffic upwards to the MX. Then the MX, when it sees the traffic is coming from 003, it will send it back to 002, because 003 and 002 actually is different aggregate Ethernet interfaces. So this will be creating a loop. If we have a traffic going this way, it will be go from QFX1, QFX2 here, and then go towards the MX and back from MX to the QFX, and there will be kind of a layer 2 switching loop here. So we say in this setup, to avoid such a switching loop, we need to avoid configuring VLAN 10, 11, 12 here, because these QFXs are actually each one is standalone, is working as a standalone switch. And we relied on configuring VLAN 10, 11, 12 here only, and we ensure that if we need to have a layer 2 reachability, this layer 2 reachability will be maintained over this link only. While in this setup, actually in this setup, here these two QFXs and these two MXs are working, both of them, each MX are working kind of an ICCP or multi-chassis lag. They are forming MC lag, and the QFXs as well will be forming MC lag. So it is mandatory, if I need to have a layer 2 communication end-to-end, I need to enable VLAN 100 here and enable VLAN 100 here. So might be a question here, there will be creating a layer 2 loop. In such a setup, there will be no layer 2 loop, because this two QFXs is actually acting as a one entity, and this two MXs is acting as a one entity. So when there is a traffic coming from here, a layer 2 traffic coming from here, kind of a broadcast or a non-unicast, the QFX will send this traffic to here, to the VLAN 100 here, and as well as it will be sent to one of these links, either 002 or 003, based on the load balancing algorithm. Let's say that QFX1 sends the traffic to Q of X2. When the traffic is being received by Q of X2, Q of X2 will no more send this traffic upward. Why? Because Q of X2 knows that this traffic is coming from Q of X1, and both Q of X1 Q of X2 have an active membership, have an MC lag interface where 002, 003 here is as well active, are member of AE1, where AE1 as well is active in Q of X1. So Q of X2 will know that already when the traffic received by Q of X1 will be responsible to sending this traffic, this unknown or this broadcast traffic, to the same aggregate Ethernet interface with AE1. So Q of X2 will stop forwarding this traffic upward. And this is kind of MC lag filtering. MC lag filtering that both MC lag peers agree that any traffic coming on the ICL link, it will not be forwarded to any of the aggregate Ethernet interfaces or any of the MCA aggregate multi-chassis aggregate Ethernet interfaces where both ICCP peers or MC lag peer are actively participating in. So the traffic will be sent this way and it will be sent upward. When the traffic is being received by MX will not send the traffic back as well to this interface. When it is received to 002, let's say, the MX will not send it back to 003 because 002 and 003 actually are members in the same aggregate Ethernet interface. So MX will not send the traffic back to the same aggregate Ethernet. It will only send it to the MX number 2. Why? When the traffic is received by MX number 2, this broadcast traffic, MX number 2, it will do the same exactly that had been done by Q of X number 2. It will receive this layer 2 broadcast traffic, but it will not send it down to any of these interfaces. Why? Because it knows actually that when this traffic is received on the ICL link from MX number 1, that there is a shared MC aggregate Ethernet interface between MX1 and Mx2. So Mx2 will not send this layer 2 traffic to any of the actively shared multi-chassis aggregate Ethernet interface because it knows that Mx1 already takes this responsibility. So now what we need here to solve all of this issue, we need to enable Vlan 100 here. While enabling Vlan 100 here, should be this reachability issues have been solved. So let's go to Mx1, Mx2. Here is the aggregate Ethernet 0. Now let's check is the reachability issue have been solved. So now we're from server number 1. Now from server number 2, we can reach the IP address of server number 1. Let's check from server number 2 if you can reach the gateway. From server number 2, we can reach the gateway. Let's do it from server number 1 to make sure if we can reach the gateway. From server number 1, now we can reach the gateway. Let's do the same for the IP version 6. Okay, so let's ping from server number 1. The IP version 6, let's ping 251, which is the IP address of Mx1, 252, which is the IP version 6 address of virtual Mx2, and 254, which is the Vrrp. Let's do the same from server number 2. Ping the Vrrp, ping 251, and let's ping 252. Let's validate the MAC address table in Q of X1, Q of X2. In the Q of X1, we have this MAC address, which is being dynamically learned from the physical interface towards the server. Let's just make the diagram back to back. So we have this MAC address, which is learned over this physical interface. So this is the MAC address of the server side. Then we have in Q of X1, we have another MAC address, which is learned from the aggregate Ethernet interface towards Q of X2, which is AE0. This MAC address actually which is learned here. It is the MAC address of server number 2. And here it is actually the dynamic remote. Dynamic remote, which means it has been learned by means of ICCP. So there is a DL and DR. DL, dynamic local, and dynamic remote. Dynamic remote, this means this address had been learned from a means of ICCP. Then we have two MAC addresses, which is being learned from the AE1. From AE1 side, we also will learn two MAC addresses. This MAC address, if you remember, this is the static IRB MAC address that we configure under IRB 100, which is being learned from the traffic that's received from AE1. And also we have another MAC address, which is 00005E, which is the MAC address also of the VIP. And this MAC address had been learned by a dynamic remote. This means that this MAC address had been initially learned by Q of X2, and then Q of X2 exchanges information with Q of X number 1 by means of ICCP. Okay, so now let's go for the MX. Let's see the Vrrp configuration. Okay, for the Vrrp, actually we have Vrrp instance running between Mx1 and Mx2, where Mx1 we configure the priority to be 101, and the VIP address, here is the IP version 6 VIP address, and here is the local IP version 6 address. Let's go to Mx number 2, do the same. In Mx number 2, the Vrrp group 100, Mx number 2 is acting as a backup, and the active and the master actually is Vrrp, is the virtual Mx1, and here is the VIP address, and here is our local address. Okay, so up to this moment we have been done with the subtask number 2, this task, and then let's move to subtask number